The first question I can kind of see is these review questions. Is that right?
Yep.
Okay. So what's the difference between average rate of change and instantaneous rate of change?
Wait, could you give me a moment real quick?
Sure.
Yeah, I'll be right back. I guess you listen to this one here. Sorry about that. Okay.
So I'm going to draw an average rate of change, and then I'm going to draw an
instantaneous is the.
What's the difference between those two?
Huh?
The top line is an average rate of change. This line is an instantaneous rate of change. So how would you explain the difference between them?
One's a secant and the other is a tangent line, and one's like an average while the other one's just over one single point.
That's a good explanation. Yeah, it's not an easy thing to explain. Okay. Number two.
Wait, could you tell me how to calculate instantaneous? Because I'm still kind of confused by that.
It's the first derivative.
Just the first derivative?
That's exactly what first derivative means, is the instantaneous rate of change.
And then you just plug in the point, and that's what you get?
Yes.
Okay.
So if I were to take the first derivative, the curved line that I've drawn here, if that was some function and I took the first derivative of it and then plugged in that point for x, say at 4, it would give me the slope of that line right there.
Mm-hmm.
Whereas I don't need calculus to come up with average rate of change. Average rate of change is the slope of that secant line. That's what average rate of change is. But slope is rise over run. And if you try applying the concept of rise over run to instantaneous, it doesn't work, because the rise is 0 and the run is 0, and you get 0 over 0. So that's why it requires calculus. As long as you're dealing with a secant line, then you don't need calculus. You can do all secant lines with algebra.
Okay.
Okay. Yeah, hold on a second. Let's see. Doesn't like it when I try to erase this stuff. All right, number 2. Complete the following statement. If dy dx is large, then small changes in x will result in relatively what changes in the value of y?
So if the derivative of...
Don't think of it as derivative. Think of it as the slope of the tangent line.
And small changes.
There's a small slope. Here's a bigger slope.
I'd probably have to go with large then for 2 in the blank.
Okay, hold on a second. If I put a graph on that small slope, then when I move over, that's dx. Well, first of all, dy dx means large. So we're looking at the pink line. That's a large dy dx compared to the black line. And what they're saying is small changes in x result in large changes in y. So this would be large. And what that means precisely is a steep slope. Always remember dy dx is the first derivative, and first derivative is the slope of the tangent line, and the slope of the tangent line is the instantaneous rate of change. All of those are equal to one another.
Okay.
If I have a curve and my slope of the tangent line is really steep, in other words, if dy dx is large, well, if I go over just a small amount on the x-axis, I go up quite a bit on the y-axis.
Mm-hmm.
So that's why the answer to 2 is large. In other words, when you have a steep slope, you don't have to go very far on the x-axis for it to be a much bigger distance on the y-axis. As you can see, there's the distance I'm going on the x-axis, and here's the distance I went on the y-axis, because it's a steep slope.
Mm-hmm. Makes sense to me.
Now, let's look at a situation where we have a small slope, like that. And they say, well, if dy dx, the slope of that line, is small, which I've drawn a small slope, that's a slope less than 1, whereas this slope here is greater than 1. Okay? So if I'm on a small slope, then small changes in x, let's say if I go from here to here, what kind of changes in y does that equal?
Not small.
Exactly, small. Not small, but small. You see why?
Mm-hmm.
In other words, for me to make, take this line over here. For me to make a big change in y, I got to make a really big change in x. Let's go from an x point from here to here. That's a really big move in x. It's this distance, okay? Well, what happens to the y value? The y value goes from there to there. It barely moves.
Mm-hmm.
This distance is the change in y. So if I make a small change, this question, I'm not convinced they meant to say small, but they did. So if I make a small change in x, I make an even smaller change in y. It's only the situation where you have a steep slope, which means dy dx is large, where a small change in x results in a large change in y. It's a difficult concept. I don't think we should spend any more time on it. Let's see. I need to move this up a little bit. What's the difference between velocity and speed of an object moving in a straight line?
I mean, velocity is how much an object moves over a given amount of time.
So is speed.
So what's the difference?
Velocity is a vector. Velocity, it's not just speed, but it's direction also.
So it's just a directional speed.
Yes. In other words, if we're talking about velocity, hold on a second. Let's see. What did I want to do here? Sorry, hold on. I can open up this page here. If we're on a straight line like that, Velocity can do this. And then reverse, go back that direction, go back that direction, and end up right there. In this case, going from here to here, that's positive velocity. Going from here to here, that's negative velocity. Going back the other way, that's positive velocity. The speed is irregardless of direction. Speed, in other words, is the absolute value of velocity. And that's the simple answer to that question. Speed is the absolute value of velocity.
Okay.
Just a second here. Define the acceleration of an object moving in a straight line.
No idea.
Well, tell me what the velocity of an object moving in a straight line is.
What do you mean?
It's the first derivative. Velocity is of the function. What we're looking at over here on the right, that's a position function. Okay? That tells me the position of a particle at any point in time. Well, that's the raw function. If I want to know velocity at any point in time, I look at the derivative of this function. And in that case, it means the slope of the tangent line. So if I want to know what the velocity is at 1, right here, if I want to know what the velocity is, can you see that point? I look at the slope of the tangent line. That's what the velocity is, whatever that slope is. If I want to know the velocity right here at 2 seconds, I'm looking at the slope of that tangent line. Acceleration is the next derivative. Acceleration is the second derivative of position. If I'm defining acceleration of an object, you could say it's the second derivative of position or it's the first derivative of velocity. Either one. They're both true. Important thing to remember. Velocity is the first derivative of position. Acceleration is the second derivative of position. Okay, number 6. An object moving along a line has a constant negative acceleration. Describe the velocity of the object.
It's decreasing.
This is a toughie. Let's look at this. Hold on a second. Let me think of how the best way to explain this is. I'm going to draw a velocity curve. Hold on a second. Now this time that's a velocity curve. This is v of t, not position. S of t would be position. Okay? So what I'm plotting here is the velocity at any point in time. Let's call that 5. Let's call that 4. So at time 0 seconds, my velocity is 4. At time 1 second, my velocity is 5. What's the velocity doing from this point to this point?
Decreasing.
So it's getting smaller. Non-negative, right? Still positive between those 2 points. It doesn't get negative until it gets on the other side of that axis.
And then it's going backwards.
Velocity is negative.
And you're going backwards, technically?
You go in the other direction, yes. Not necessarily backwards, because sometimes you're going up and down. And up is positive velocity, down is negative velocity. Okay? However, if my velocity is positive but decreasing, what's my acceleration doing?
Wait, could you repeat that?
If my velocity goes from 5 to 0, what is my acceleration doing?
It's decreasing.
Correct. But it's not, it's decreasing. Okay? Now, this is what's complicated. If you get on the other side of the line, what's my velocity doing from this point to this point?
You're moving it. You started moving in another direction.
But notice that it's increasing velocity, right? The speed is increasing.
Yeah. The farther away from
the velocity right there equals 0. So I went from a positive velocity of 5 to a velocity of 0. That's deceleration. I'm stepping on the brakes. So acceleration is negative here. A of t is negative in this area right here. Now, get to where my velocity is 0, which means I'm stopped. And I turn around and I start going the other way. Well, this is minus 1. This is minus 2. So I go from a velocity of 1 to 2. My speed is increasing. What's my acceleration doing between here?
It's increasing, technically.
Yes. That's what's hard about this, is that when you look at a velocity curve, the velocity is down the whole way. But the acceleration is decreasing down to the 0 point, and then it's actually increasing the rest of the way. So you really have to have a good grasp of this to understand this part of the equation. And this is really more advanced calculus that I'm not quite sure you're quite ready for. They should really start you off with movement along the x-axis of a particle. And then they should ask you all the appropriate questions. When is the velocity increasing? When's the velocity decreasing? When is the acceleration increasing? When is the acceleration decreasing? And then it's a little easier to understand. To jump right in with this problem at this stage doesn't seem to make a whole lot of sense to me. It's too difficult to understand.
Okay.
Okay? We'll get back to those kind of questions. Now, let's look at number 7. So this patrol car is going vertically on a north-south freeway. This is north. Okay? So at that time, 9 a.m., he starts heading north with this position function. In other words, whatever that function is, and they're not giving it to us, but they are showing it to us over here. Okay? What we're looking at is s equals f of t. That is a position function. All position functions usually begin with s, velocity functions are v, and acceleration functions are a. Assume s is positive when the car is north of the patrol station. So if we look at this car over here, here's when he leaves. That's 9 a.m. And he's heading north. Got to be a positive velocity, right? Determine, the questions they're now asking is determine the average velocity of the car during its first 45 minutes, which is right there. In other words, the position changes from 0 to 30. First of all, you see why that's the 45-minute mark?
Yeah.
Because that's in hours. So the 45-minute mark is the 3/4 hash mark. In other words, from 0 to 45 minutes, he goes 30 miles. So what's his average velocity?
Would you take 0.75 minus 0 in the denominator, and then 30 minus, just 30 over 0.75.
It's the difference in the y. Remember what average velocity is. It's just the slope between 2 points. So the average velocity is that right there. It's rise over run. That's always what average velocity is. So it's the position function at 45 minutes minus the position function at 0, all divided by 45 minutes minus 0. Okay, now S of 45 is 30, S of 0 is 0, and when I put everything in hours, that comes out to be 0.75. So I really have 30 divided by 3/4 of an hour. What is that?
120? No.
How do you divide by a fraction?
Oh, so it would be 40.
Okay. So that's his average velocity in the first 45 minutes is 40 miles per hour. Because I turned that into hours, that's miles. So it's 40 miles per hour. You with me?
Yep.
Okay, let me erase all of this. Find the average velocity over the interval 0.25 to 0.75.
So it'd be all over 0.5. Sorry, I'm thinking.
It's all right. Remember, the numerator is the difference of the y values.
So it'd be 20 at the top.
You got it. Now what's that turn into?
That would turn into 40.
So his velocity was the same in the first 45 minutes as it was in the 15 to 45 minute range. Is the average velocity a good estimate of the velocity at 9:30? Right there is 9:30, okay? Well, the average velocity goes from there to there. Well, if we look at 9:30 and try to figure out the instantaneous velocity, that looks awfully close to the tangent line, right? So the answer is yes. Is the average velocity a good estimate of the instantaneous velocity at 9:30? When they ask the velocity at 9:30, that's by definition the instantaneous velocity. Because that's at a moment in time, which would be the tangent line, the slope of the tangent line. Well, to me, our average velocity line looks just like the slope of the tangent line if I were to draw it. So At this time, yes, the average velocity is a good approximation of the instantaneous velocity. It isn't always, but at that point, it is. Okay? Now let's keep going. Find the average velocity of the car over the interval 175 to 225. Okay, so the denominator again is what?
Wait, what?
Okay, we're trying to find the average velocity here. Well, here's the y-coordinate at 175. Here's the y-coordinate at 225.
Oh, so you take 225 minus 1.75.
That gives you 0.5 in the denominator. That's the run. That's the x change. What's the change in y?
It would be negative 10. No, negative 13, I guess.
Okay, remember what the change in y is. It's f of b, the second point, minus f of a, the first point. This is f of b. What's f of b?
Negative 13.
Oh, okay. I'll go for that. Minus, what's f of a?
I would go 15.
Just 15, positive 15.
Now that should negative 28 over 0.5. And that should give you 56, negative 56
miles per hour. Now, what that means is that from between those two times, he's going 56 miles an hour, but he's going back south 56 miles per hour. In other words, what he's doing, let's look at his trip here. He starts out going north. He goes north for 35 miles. Then he stops right there at maybe right there. He stopped because the slope of the tangent line is 0. The slope of the tangent line is the velocity. So if the slope of the tangent line is 0, he's stopped. And then from this point all the way down to here, he's headed south. He's no longer headed north. He's going in other words, the velocity, hold on a second. Yeah, in other words, he's 35 miles away from the patrol station, comes back, now he's no distance away from the patrol station. So he definitely has to be headed back south. Okay? Takes him a little over an hour to get to that 35-mile marker point. He stops his car, he turns it around, he comes back the other direction, and it takes him a little less than an hour to get back to the patrol station. Now, his distance, in other words, if I were to want to know his velocity, his average velocity, I would take the slope of the secant line. If I want to know his instantaneous velocity, I take the slope of the tangent line or the first derivative. It's very difficult to understand, incidentally. This is one of the harder parts of calculus, is understanding the relationship between position, velocity, and acceleration. Okay, so we figured out the average velocity over that interval. It was minus 56 miles an hour. Estimate the velocity at 11. Precisely 11 is that point right there. What do you think his velocity is at 11?
I'd probably go with negative 50-ish.
Negative 56, yeah. In other words, what we just figured out was the average velocity between that point and that point, which is the slope of that line. And if we were to try to figure out the slope of the line precisely at 2 hours, well, it's going to be the slope of the tangent line, which looks to me to be virtually identical to the slope, the average slope, right?
Mm-hmm.
So in this part, the average is pretty much the same as the instantaneous. Same thing with this part. There are places on this graph, though, where it is certainly not true. For example, from there to there, what's his average velocity?
Wouldn't it just be 0?
Yes. What's his instantaneous velocity at the 45-minute part? Whatever that is, whatever the slope of that is. It's certainly not 0. And what's his instantaneous velocity at the ending part?
Not 0 either.
Exactly. The same as this one, only in the opposite direction, negative. So here, the average velocity would be that. But no matter where you're at on that line in the upper area, in that area right there, the average velocity is not going to be the same as the instantaneous velocity except at one point right there. In other words, the instantaneous velocity there is 0. And the average velocity there is 0. And the average velocity there is 0. But there are certainly places in there where it's not. In other words, near the top is not at all the same as on the sides. They started us off with there, where the average velocity is pretty much the same as the instantaneous velocity no matter where you're at in that interval. When I look at this interval, the average velocity is pretty much the same as the instantaneous velocity, no matter where I point to. All right. Describe the motion of the patrol car relative to the patrol station between 9 a.m. and noon. All right. 9 a.m. is right there. Noon is right there. He goes from being at the patrol station. Where's that?
At 0.
No, not. When I say where is that, I mean what's the y coordinate of that?
Oh, that one?
Mm-hmm.
Oh, it's not at the patrol station, my bad. It's 3, negative 15.
Which means 15 miles south of the patrol station. That's the answer. 15 miles south of patrol station. It's not just negative 15. It's describe the motion of the car relative to the patrol station. Well, in fact, we haven't. Okay, let me make my answer a little bit more detailed. Between those two times, between time 0 and time 3 hours, our patrol car goes north for 35 miles. Then it goes south for 63 miles. This whole thing from there to there is that patrol car going south. Okay, and it goes south by 35, plus it goes another, well, it only goes south by 15 by the time I reach noon. You see why that point is noon, right? That's where time is 3 hours. He left at 9 a.m. So the 3 hour mark is noon. Well, where's he at noon? 15 miles south of the patrol station.
Okay.
Everything underneath this is going to be south of the patrol station. Everything above it is going to be north of the patrol station. All right. Go to the next page. No, I did it okay. Yeah, these particular concepts are far harder than just doing derivatives based on power rule, product rule, and all those things. Mm-hmm. But it's an important part of calculus, and you gotta try to understand it. Just always remember that when I put the three curves up, I put function at the top, I put velocity right below it, and I put acceleration below that. Mm-hmm. That's what this is. The top curve is position, the next curve down is velocity, and the next curve down is acceleration. This again is position. It says position and time. Okay? So on number 8, let's answer the questions. Now notice that Seattle to Minneapolis, ooh, that might be a horizontal line. Yeah, that might be going like that. I'm not sure that it matters. Let's read it a little bit more. First of all, T is the number, or F of T is the number of ground miles from Seattle T hours after it takes off at 6 a.m. Notice that after 8.5 hours, it returns to Seattle. Well, there's Seattle, position miles from Seattle. When I take off, I'm 0 miles from Seattle. At some point, I get to be like 1,500 miles from Seattle. Then I stay 1,500 miles from Seattle. And then I start turning around and coming back to Seattle. And by 8.5 hours later, I'm 0 miles from Seattle. Okay? Mm-hmm. Okay, let's answer the first question. Give me the average velocity during the first 1.5 hours of the trip. Well, that's from that first X to this point. And if we go up on the y-axis, after 1.5 hours, where am I relative to Seattle?
600.
600 miles from Seattle, exactly. So what's my average velocity?
I go with 600 over 1.5.
Good. And that's 400 miles per hour. And notice that it doesn't matter if it was on a horizontal line or a slanted line. Don't care. At no point did the plane turn around and go back the other direction during mid-flight. In other words, what's happening right there? What's the plane doing?
It's in Seattle. Well, it's in Minneapolis, or?
Yeah, it stopped. In other words, the position's not changing. It got to 1,500 miles from Seattle, and it's still at 1,500 miles from Seattle. And the tangent line is 0, so the velocity is 0, so it's stopped. It's at the terminal in Minneapolis. And at this point, it takes off and goes back the other direction. Still has positive distance. Well, no, that's a negative velocity. Remember the relationship. Very important to remember the relationship between, Here, I'm going to bring it up again just because it's so important. Sorry, it's going to take me a minute or two to find it. One of the most important things is, not that. Here is the original function, okay? Here, let me write on this. Think of this as the position function. That's s of t. Think of this as the velocity function. That's v of t. And this is the acceleration function. In other words, this middle graph is the first derivative of the top graph. The bottom graph is the second derivative. The key things to know when you're looking at functions and their derivatives is when that function is increasing, you see those two pink points? The first derivative is positive, always. And you can see that it is. The velocity is positive between those 2 points. It's decreasing, but it's still positive. It's above the x-axis. Now, when the position goes from high to low, in other words, the position function is decreasing. You know what I mean by increasing and decreasing. When the position is decreasing, the velocity is negative. That whole area right there is negative velocity. It's below the x-axis. And when the position function starts increasing again between those 2 points, well, the velocity turns back positive. Notice where the velocity is exactly 0. Right here and right there. And if I go up to the position function, the slope of the tangent line is precisely 0 at those 2 points. Now, to carry that thinking down to the second derivative is all you really have to do is think of that as being the first derivative of that. And the same rules apply. When this function, whether it's the first derivative or whether it's the original function, doesn't really matter. When it's decreasing, this is negative. That's negative acceleration. It stops right there, which is that point there. Acceleration is 0. Why? Because the thing has stopped. Then the thing starts increasing again, so its first derivative is positive between those 2 points. So always remember that increasing means first derivative is positive, decreasing means first derivative is negative, and not increasing or not decreasing means first derivative is 0. And that only occurs at those tangent lines that have a 0 slope. No other point on that top function has a 0 slope, only those 2 spots. Notice that that's a relative maximum and that's a relative minimum. So what we're discovering is a technique for finding out where the relative minimums and maximums exist on a function. So all you got to do is take the derivative of the function, set it equal to 0, and you find that spot and that spot on the x-axis. All right, let me get rid of this and go back to where we were. All right, So where are we at here? We calculated the average velocity. Hold on. Calculate the average velocity between 130 and 230. Can you do that?
Yeah.
I don't want to spend time doing it if you now know how to do it. We're not covering a lot of material here, so I don't want to keep doing the same problem over and over, which is what they're asking us to do. Okay, so let's look at C. At what time is the velocity 0?
From 3 to 5.
Yeah, approximately. From this point here to that point there on the x-axis, since they said what times is the velocity 0. And notice that that's it. No other place on that curve can I find a horizontal slope, whether I'm talking average or instantaneous. But certainly there is no slope of the tangent line that is 0 except anywhere between 3 and 5. That's when it's stopped. That's what a velocity of 0 means, is it's got to be stopped. Okay. Determine the velocity of the airliner at noon, which is t equals 6. What's that velocity?
No, negative.
Well, it's
No.
negative because that's a decreasing function. So
Yeah,
the first derivative is going to be negative. But we're talking about a tangent line that's going to look something like that, right? So if you had to estimate it, how would you estimate it? Find the average velocity. Or find the slope of that pink line. Well, you can use any 2 points to find the slope of that pink line. Let's go between 6 and 7. Okay? So what is the average velocity between the 6th hour and the 7th hour? In other words, that to there.
It would be, so it'd be 7 minus 6, so it'd be 1 over 1.
Okay.
And it would be 600 minus 1200, so negative 600.
Good. So the speed is 600 miles per hour. The airplane's flying at 600 miles per hour. But the negative sign indicates why is the velocity negative? Because it's going back the other way. In other words, it's getting closer to Seattle. And like I said, it doesn't really matter if on a map, if I draw a map of the United States here, if Seattle to Minneapolis is a straight horizontal line or not. Even if Seattle to Minneapolis was like that on a map, well, you would still call that positive velocity and you would call that negative velocity. So it's not quite correct to say that positive velocity is always to the right or up. In the context of the problem, positive velocity is in the direction of Minneapolis, whereas negative velocity means you're flying from Minneapolis back to Seattle. And I don't care whether it's on a horizontal line on the map or not. Doesn't matter. And I can understand why that's probably a little confusing also. But let's go on. Okay, 9 through 14. Okay, finally we get some math problems here with 10 minutes to go. It's okay. This is what's going to be more valuable to you, I think. Okay. This is the position function. Okay. Suppose the position of an object is given by S equals f of t, where S is measured in feet, S is greater than 0, corresponding to positions right of the origin. So this is an object moving horizontally. So this is the classic problem where we have a particle moving along the x-axis. Okay? And its position is given by that. Well, the graph of that function is, let me redraw that. If I draw a position function based on that function right there, it's a parabola, is it not?
Uh-huh.
And I believe it's a parabola that basically goes like that, where t goes only from 0 to 5. Now, let's see, I haven't drawn it correctly. Oh, I know why. The vertex has to be at 0. So the true way to draw that is a parabola like that, okay? But notice our domain is restricted. We're only restricted from there to there. Why? Because you can't have negative times, ever. Time is always positive. So if I want to erase, in other words, that part of the curve is not critical. Only part of the curve we're looking at is to the right here. So there's the graph of the position function. This is s of t. This is t. With me?
Mm-hmm.
Find the graph of the velocity function. Well, tell me what the velocity function is. Let's figure it out mathematically.
Don't we just find the derivative?
Yep. So v of t is what?
Would it just be x equals y pretty much?
Take the derivative of that function. You know how to do that. Use the power rule.
Yeah. Oh, gosh, yeah. So it'd be 2t minus 4.
Okay. Now, if I graph that in green on the same curve, I could try to graph it below it, but I don't really have enough room. So I'm going to graph in green 2t minus 4. Well, minus 4 goes through that. 2t is a slope of about that. That's my velocity curve. Okay? Now, let's see if that makes sense. Right there, the slope of the tangent line is 0. I've drawn that first curve incorrectly also. In other words, its y-intercept on the parabola is down here. And let me redraw this just to be exact.
Okay.
First curve is like this. Goes through this point right here at minus 4. Okay? The first derivative curve in green also goes through that point and has a slope of 2. So that's the velocity curve, is the green curve. That is v of t. And now let's check and make sure that makes sense. Well, what is v of t when time is 0? Minus 4. Remember what v of t is. V of t is 2t minus 4.
It would be negative 4.
Right, and that's exactly where that is. Remember, this is the time curve here in both the pink and the green.
Mm-hmm.
But the pink is s of t and the green is v of t. Okay? Now, notice that the slopes of the tangent line start to go steeper as I go to the right. So what does that mean? That means my velocity is increasing. As you can see that it does. It goes from -4, straight line, up and to the right. So whatever my y-axis is, that's the velocity, and I can tell that my velocity is increasing. So graph the velocity function. When is the object stationary?
It would be stationary at
Time.
2.
Yeah, very good. In other words, whenever the velocity is 0, that's when it's stationary, right? So I set that equal to 0 and I solve this equation. And I get at time 2, the velocity is 0. Well, if I go over here to my velocity chart, that's where the velocity is 0, and that's at time 2. So that makes sense. When is it moving to the right?
What do you mean?
Remember what we have here is a particle moving along the x-axis. It moves right, and then left, and then right sometimes, left sometimes. It's got to stop for it to switch from right to left. So this part here, it's going to the left, right? Because the velocity is negative. Velocity is 0 where my x is, so it's stopped right there. And then to the right of 2 hours, the velocity is positive.
And that would be when it's going to the right.
Exactly.
Okay.
Okay. So it's moving to the left between 0 and 2 hours, and then it's moving to the right 2 hours and greater.
Okay.
Determine the velocity and acceleration of the object at time equals 1. Well, this is actually much easier to do without the graph. Remember what acceleration is. Well, first of all, velocity is equal to 2t minus 4.
So wouldn't acceleration just be 2?
Yes. So, determine the velocity at t equals 1. What is the velocity? What's v of 1?
-2.
Good. So v of 1 equals -2. What's a of 1?
Just 2.
Yes. There's no variable. So a of 1 is that constant, 2. Acceleration is 2 no matter where you're at. The acceleration is positive. Throughout the entire time frame, from 0 time, and remember what the velocity curve looked like. It looked like this. And yet the acceleration is constantly 2. Even when the velocity is negative, the acceleration is positive 2. Why? Because it's going from a negative velocity slowing down. That's actually positive acceleration. And then, of course, the rest of it. In other words, this velocity curve is increasing the entire way, right? Well, if it's increasing the entire way, then its first derivative has to be positive the entire way. And it is. It's 2, which is a positive number. No matter what time you're looking at, the acceleration is positive 2.
Okay.
Okay. Let's see. Okay, we've hit 5 o'clock, and unfortunately I have more sessions today. So,
Okay.
on Jake. But yeah, this is tough stuff here. This position of a particle moving along the x-axis. That's how these are usually described, and it's real tough to get a handle on them.
Well, I get it fairly well though, so thanks.
Good. Good.
Yeah.
Okay. I'll talk to you next time.
All right, see you.